I'll try to maybe skip a few slides to get us back on mineral exploration timescales. So that's us. Right. So why do we do geophysics? And it's the needle in the haystack problem. The aim of geophysics is to reduce the size of your haystack. And also, how do you know if your drill hole maybe just missed something and could be just 5 meters away? Geophysics is one way to avoid the near miss problem. So what geophysics do we need to use in our project? And that can seem like a really big question, but it can be downloaded or distilled into a basic question. Is there an appreciable physical property contrast with your host rock? So is it more conductive? Is it likely to be more magnetic? Is it likely to be more dense? Is it more chargeable or more reflective? And the answer to each of those questions gives an indication of which sort of geophysics might be appropriate. Now, that doesn't necessarily mean the geophysics is appropriate, but it means you're at least starting in the right area. So today we're looking at electrical methods, and really the most common ones used in exploration in electrical geophysics are EM and IP. IP is actually a conglomerate of two methods, that's resistivity and IP. So once you've worked out that you definitely need an EM or an IP survey because you think you're going to have mineralisation which is either chargeable or conductive, then you need to talk to an experienced geophysicist, one who's impartial and obviously experienced in that particular type of geophysics. And then you need to ask them questions. Your job is not to know these answers, but to actually ask these questions. And that for me is the difference between an experienced or a good exploration team is someone who knows what questions to ask. They don't ever have to know the answers, but they need to know that ask the questions. And they ask me all these questions quite early on in the process. And that really is one of the main ways I can tell if someone's done a geophysical survey before or not. So today we talk about the fundamentals of EM and IP. And then depending on how much time I've gone through, we'll go through some real life projects. And that's hopefully we'll get to use the poll functionality in Teams, which is good fun for everyone really, because instead of just being a passive absorber of what I'm talking about, you get to actually click on it and interact with the presentation. So let's talk about firstly the fundamentals. I've got no sign of time anywhere, I can't tell what time it is. Somebody know when I'm halfway or I've done 30 minutes? Yeah, okay. All right, so how do EM work? Well, you can think of it as EM is a great big metal detector. That's essentially, it uses the exact same physical properties. Now, this can be distilled into two elements. You've got a transmitter generating the electromagnetic pulses. In this case, it's a transmitter loop laid out on the surface, this big rectangle. I hope you can see my mouse. Nope. Definitely can't see my mouse. No, there it is. Laid out on the surface, and then you've got around that transmitter is generating this electromagnetic field called a primary magnetic field. It's actually a magnetic field just the same as the Earth's field, but unlike the Earth's field, it's a changing magnetic field. And did you know that every single basically electrical current has a magnetic field? So the power lines have magnetic fields, these lights have magnetic fields, everything has magnetic fields. And every magnetic field, when it's changing, generates currents. So they're one on the other. That's how we can use magnetometers to measure electrical currents in the ground. It's the interaction between electricity and magnetic fields is basically the fundamental of EM. So this electric loop, which is just a loop of wire, usually insulated wire because it'd be messy if it wasn't, and it has electrical current flowing around it, and then that current is turned off as fast as we can make it turn off. And by the fact it's turning off, that causes a changing magnetic field, and wherever that field intersects anything conductive in the Earth, and of course it's spreading out through the whole Earth, so it intersects everything, it will generate secondary electrical currents because changing magnetic fields generate electrical currents. Just like these lights here would be generating an electromagnetic signal in anything conductive in this whole room, electromagnetic impulses generate currents in the ground. And these little currents have their own secondary magnetic fields associated with them. And if we have a receiver, in this case the receiver is going down a borehole, we can measure those magnetic fields. if we have our receiver going along the surface, then that's a surface EM survey. And because the transmitter loop is not moving, that's a fixed loop surface EM survey. If we move our transmitter along as we move our receiver along, that's a moving loop EM survey. And guess what? If we put the whole lot underneath an airborne EM system and fly it along, then that's airborne EM. We're not very creative with our terminology, but it pretty much says what it is. So airborne EM is just moving loop EM done really, really fast. The transmitter, secondary fields go pulse, 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 and we measure them with our receiver. So what are our actual fields? Well, now this is our transmitter loop. Imagine a cross section through our transmitter loop. What are our actual fields actually doing? So our current is in our transmitter, and at this point here, what's happening? Well, it's just turning off as fast as it can. So the current in electricity is turning off, going down to 0 as fast as it can, and that causes a pulse in the ground. So, and this is the voltage. If we had a receiver somewhere on this surface, it'd be measuring a voltage related to that pulse in the ground. And then after a bit more time has passed, that current or that voltage, the current flowing through the ground has spread out and gone down into the earth a bit more. A bit later in time, it's spread out a bit more. And if you can imagine, this looks exactly like you've taken a cross section through a smoke ring. Someone's blown a smoke ring and you're looking at a cross section through that smoke ring, and that's how it spreads out in time. As your transmitter's flying along, essentially that's what it's doing. It's going poof, 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 blowing smoke rings into the ground of electromagnetic energy. And wherever there's a conductor, you'll cause lovely little fields to be generated. So I'll show you what that looks like on this video. So this is what our receiver would be doing if we had a whole bunch of receivers on surface. And you can see the transmitter's just turned off and our electromagnetic energy is spreading out into the ground. And notice this little white thing over here, that's actually a confined conductor. So you can imagine our fields are spreading out into the ground. The confined conductor here could be a massive sulfide ore body. Imagine that's a massive sulfide ore body. And the fields are spreading down. Most of the fields are just spreading down into the ground, diffusing away. This is called diffusing into the ground. And obviously, if you've got conductive overburden in an area, these fields will be stronger because the electricity is more easily trapped by that overburden. But notice what's happening over here now. Now, most of our fields are spreading out and just going away, diffusing away like a giant smoke ring, just disappearing off. But see what's happened in our confined conductor. They're still ringing, if you like. They're still trapped in this area. So now our conductor is the only thing that's left over. So that's what we're looking for. And you notice that it took a long time. So at early time, we had fields everywhere. But just after the transmitter had turned off, we had fields everywhere. But at late time, which was what we're at now, there was only one field left, and that was what we were what was from our massive sulfides. And so when geophysicists talk about late time conductors, that's what they're talking about, okay? It just means that the signal took a long time to show up, so it's a late time, all right? And that's an indicator that it's a good conductor. So what? EM maps conductivity. What is the control on conductivity? And it's complex. That's why I can't say that your VHMS is always going to be an EM conductor. So firstly, you have texture and mineralogy. Sure, you can have a bucket ton of sulfides, but if it's a brecciated ore body and there's no interconnection between the different lumps, then effectively it's not a conductor. So texture, the things need to be interconnected. Imagine if you had trying to wire your house together, you need to have both ends of the wire meeting up. And that's the case for brecciated ore deposits, like lots of little chopped up bits of wire, it doesn't work. We need to have interconnectedness between our individual grains, and on the mesoscale and macro scale, the whole lot has to have electrical continuity. So sometimes it might be good on the core scale, but then when you come across to the whole ore body, it's not electrically continuous. So how does that apply to mineralogy? Well, pyrite and galena are strongly crystalline, which means they often actually, even though they're quite high-grade sulfides and do conduct electricity well, when you have them on a large ore body, they're not actually that conductive because they're very crystalline. And then pyrrhotite and chalcopyrite are the opposite. They're very amorphous. So something that might be 30% pyrite is usually a conductor, but let's say 15% pyrite might not be a conductor, but 2% chalcopyrite would be. So you can't just say, it's got high-grade sulfide, therefore it's going to be an EM conductor. Electrical continuity is very good. Pyrrhotite is a really, really winner. I find a lot of pyrrhotite. Next thing is weight percent sulfides. Generally above about 3% sulfides is when you start to see a precipitous drop in resistivity, so increase in conductivity. Conductivity and resistivity are the same, except the inverse of each other. So if it's high resistivity, it's low conductivity. Notice it's a logarithmic scale. So, and that's just the nature of this particular unit. It doesn't obey those lovely linear things that we understand intellectually as humans. Logarithmic scale, okay? Once again, pyrrhotite and chalcopyrite are overall very good contributors. So you can have a zinc ore body, which is technically not conductive, but it has a bit of pyrrhotite associated with it. Suddenly you've got a winner. You can detect it with EM. So no assumptions. Just because it's not necessarily what you think, something like a bit of pyrrhotite can really help. So what's an example of EM? So this is a really basic and just really common day-to-day. I do this sort of stuff really every day, okay? So we've got a barren drill hole. We haven't intersected anything. And this team, because they're not in a panic, know that that's not the end of the world because they do some downhole EM. This is looking for nickel deposits, so these things are very, very small. And downhole EM shows an off-hole anomaly, and I can tell from looking at that thing that it's quite close. It looks like it's within probably 20 metres, 30 metres of the drill hole. The cross components, which the U and the V component, give our direction to it. So I can tell it's away from the hole and it's approximately above the hole. And the next drill hole is targeted on the plate model. So that looks something like this. So there's the plate model, drill hole, and that shows a clear intersection response, and it's intersected a massive matrix nickel sulfide posse. So that's a really typical use of EM in nickel deposits. Pentlandite is a lovely conductor of EM. It's an absolute screamer. So for the nickel mines, they actually install their loops permanently and basically do downhole EM on probably every second hole, I'd say. Sometimes they install permanent underground loops as well. So EM is by far the sharpest tool in the exploration geophysics box. So unlike lots of things like magnetics, where you have magnetic anomalies everywhere, often I'll see a whole EM survey and there's no anomalies. And that's because there's only one thing that responds to EM, and it has to be really, really, it has to be there. So it's basically massive sulfide or graphite, essentially, or pyrrhotite, So those are the three things. And if you don't have any of those things, you don't see anything. Lovely thing is we can do it airborne because we don't need any form of electrical contact with the ground. So we can cover the huge areas quickly and jag something. It can be used up to 1,000 metres below surface to detect something that deep below surface, but something at 1,000 metres below surface has to be enormous to be detectable with EM. The size has to be roughly proportional to your depth to have any chance of being able to see it. And for downhole EM, I've seen conductors up to 400 metres off hole, but in generally the range of investigation is 100 to 200 metres, depending on how big your target is. So why would you not use EM? If you've got lots of really conductive overburden, that can make it really so you can't, essentially all your energy stays in the overburden and it hides basement responses. Or if you don't think your mineralisation is conductive, disseminated sulfides is a good example of that. If you think your thing's too deep with respect to its size, or if you've got lots of power lines and things like that on surface. So all right, so there it is. Thank you. Right, so I've spent 6 minutes. That's pretty good. Okay. One thing I want to show you, but I'm not sure if it's that interesting, is actually what the hell is an EM profile. So I see lots of people displaying EM data as pretty maps, and it's really not designed to be displayed as pretty maps. Because of the exponential nature of this signal, you actually inevitably can't see what you're looking for in map format. So drilling EM targets based on a map is a big no-no. We sometimes display it as maps because we need to have maps in our reports, but it's actually don't look at the data in map format. EM data is designed to be, it's not designed to be, it is displayed as a profile, and that's where we actually recognise conductors. So this is what raw EM data looks like. So we've got our transmitters on. We're actually not interested in that piece of information, but the receiver's going all the time, so may as well record it. Transmitter's off. That's the part where we're interested. That's where our fields are spreading out through the ground and we're measuring. Transmitter's on in the opposite direction. Transmitter's off. So it just does square waves. If we did 4 of these in 1 second, that'll be a transmitter frequency of 1 hertz. So each of the on time, 250 milliseconds, 250 milliseconds, 250 milliseconds, that's 1 hertz. So that's the frequency right there. Depends on the amount of time that takes to do one of these. Then we take each one of these single groups of 4 and we add it to the next one and the next one and the next one. And if you add that together 96 times, then that's averaging 96 times, which is stacking 96 times. So you could say that's 96 stacks. And that's what it looks like once you've stacked it. So you can see instead of just jagger, now we've got, you can see the on time and you can actually see the beginnings of an EM decay here in the off time. But this is still really jaggedy. You can see how much up and down there is. So we want to get what the actual EM signal looks like, that lovely decay over time. So we take the first little fraction of data and we average that together on this and we bin it into Windows. So we essentially divide this up all into little segments over time and bin that into channels. And each one of these bins is called a channel. So you'll see in geophysical reports, they say channel 1, channel 2, channel 15, channel 25, channel 35. That's referring to which little segment. So the first one is here, the last one is here. So channel 1 will be here, channel 36 be there. And channel 15 and I spread all through the middle. And then essentially this raw data bins into a series of channels. Now, if we just took this first instant right here after the transmitter is turned off, that's channel 1, we'd have just 1 dot on this decay here. So that'd just be channel 1 would be there. So I flip it up the other way. So that would, and so we could go along and just measure at one point after the transmitter how much signal is in the ground. And we don't do that because we do more. So we do it for 36 channels. Essentially, so this shows you all the time that the transmitter's lost how much signal is in the ground. Now this is a linear scale, which is no good for anyone, so we display it on a logarithmic scale. So channel 1's up here, and channel 33 in this case is down there. So that's a single reading like that. You've stopped at one point and you've taken a single reading. So how do we turn that into an EM profile? So imagine that this single reading is this one right here. So imagine channel 1 is that point there, and we just took a single reading at 300 meters downstairs. That would be where my cursor is right there. And then we moved the receiver further 10 meters down and took that single 1 point there. The channel 1 is there, and then we just join them together. That's how we get that little bit of line. We repeat that all the way down the hole. And that causes basically we'd have a map of channel 1, of the way that channel 1 varies down the hole or along the surface or beneath the airframe, whichever way you're doing it. And so this first line on the EM profile just reflects the instant after the transmitter turns off, all the way down the hole. The second line reflects slightly later after the transmitter has turned off and how that varies all the way down the hole. So the EM profiles are basically a way of displaying 4-dimensional data in a 2-dimensional profile form. So we're displaying time and amplitude versus distance. So that is really important because that way we can see how the signal varies. We're only interested in where these late time signals bump up, where they are anomalous, different, geophysically anomalous. So let's look at this. It's a very sensitive mouse today. Let's look at this profile here. This is an airborne EM profile. We've got our early time response there, which is the channel 1, which is right after the transmitter varies. And you can see that that's basically mapping variations in overburden, which is not that much interest of anyone. Obviously, the overburden gets rapidly thinner right here. That is not an anomaly. That's just an indication that the overburden is thinner, and then it gets thick again. This down here is where we're interested in. This is a late time conductor. That is an anomaly. And it's actually some pyrrhotite, but it is not overburden. So you can see that the pyrrhotite doesn't really show up in these first few channels, but it certainly shows up when we get to these late time, which is a long time after the transmitter turned off. Long time being still in the order of milliseconds, okay? So So this style of presentation displays both the temporal and spatial characteristics of EM, and that is how I look at EM data. So what sort of EM should you use? Well, it really depends on what scale you're looking at. If you've got hundreds of line kilometres of remote district with no ground access and really no idea, then you do an airborne EM survey. Airborne EM is cheap, $200 per line kilometre, something like that. You might find something. But if you have maybe sort of a bit more of an idea, you've got a really good geochem anomaly, you know there's some good conductors in this region and it's not such a big area and access isn't so bad, then maybe consider a moving loop EM. At the prospect scale, when we've got like a couple of kilometres strike length maybe, and you really know your geometry, then you can do fixed loop EM. Fixed loop EM has one downside on moving loop, has one benefit of downside of moving loop. It's cheaper than moving loop, but it doesn't care the orientation. Moving loop is agnostic regarding the orientation of your conductor. Fixed loop, you need to have your transmitter loop in the right location, otherwise you won't energize it. And then, of course, downhole EM, the application of downhole EM is whenever you have a drill hole near something that might be conductive. I do lots of downhole EM defining mineralization in near mine stuff, so, you know, even in mine development. So let's move on to IP. So how does IP work? So IP has two surveys. It's an induced polarization and DC resistivity survey. So what is it? And let's do some very basic concepts. So first, let's talk about DC resistivity, because that's the easy one. That's really just how well the ground can transmit electricity. Obviously, the amount of sulfides, because sulfides are highly conductive, affects this. But the other thing, the main thing that really affects it, lost my mouse again, is the porosity of the rock. So sulfides affect it, but really what we're mostly mapping with DC resistivity is porosity. So also salinity. So the main exception to this is sulfides and graphitic shales. This is an example of a DC resistivity survey trying to find hard versus soft rock from a perspective of doing like building a road or something like that. And you can see here that, you know, the low porosity rocks like granites and a fresh basement is quite well defined by the resistivity in this saprolite zone. In this case, high resistivity is red. We geophysicists, to make it really lovely for you guys, randomly flip this colour scale for you. So sometimes red is low and sometimes red is high. You have to look at the colour scale because even I don't know half the time in my own reports. So you have to put the resistivity colour scale in there for later on. And then saprolite is obviously low resistivity. So you can, just by using this, you know that this area is they're not going to have any problems with doing the cutting, but these areas they might have some problems with cuttings. Really what? Right. A few seconds. That could be interesting later on. Okay, so DC resistivity, how do we measure it? It's very simply, we've got electrodes plugged into the ground and we pump electricity into the ground, which isn't that radical. We're doing that all the time in most of our housing buildings and things like that. And when we say electricity, it might be 1 amp, 2 amps, 5 amps. Sometimes it makes worms come out of the ground. That's about the most exciting thing I've seen. That can be maybe 100 metres, 200 metres, 5 metres. It depends on what you're trying to resolve, the distance between these two electrodes. And those electrodes are basically lumps of metal that we bury in the ground so you can have the electricity actually make it from the transmitter into the ground. And the electricity just doesn't follow a straight path. It actually spreads out through the ground in this sort of fashion, the way these arrows are drawn. And then we measure, using the world's most expensive multimeter, the resistance and the voltage between these two electrodes. So you could even use your little home-based thing that you measure your batteries with, except it wouldn't do a very good job. But just measures basically the voltage between these two electrodes related to this electricity spreading through the ground. So it's very, very simple. And you do that when the transmitter's on. So now what's IP then? When we talk about DC resistivity, IP is the other part of it. So in DC resistivity, this is what you're measuring with your multimeter. It's just a simple resistance of a voltage equals voltage divided by current. Now, the ground doesn't behave like a perfect electrical system. The ground actually has capacitance, which means it stores the electricity like a capacitor. This means that if you turn this transmitter off, the voltage doesn't immediately go to zero. The voltage takes the time to go away. Technically, if you turn the transmitter off, there should be no voltage, right? Except the ground doesn't do that. It actually stores the electricity like a little battery, and then it gradually releases it. So with IP, we've got this, and what we're measuring is this capacitance of the ground. You might, some people even refer to it as capacitance. And why is that? And that's because conductive metallic grains in the rock fractures disrupt the ionic current flow, and they act like millions of microscopic rechargeable batteries. So you actually get these little polarization across the sulfide. So the positive ions go to one side of the sulfide grain, the negative goes to the others, and then they can't travel back at the speed of light back to their original position. They take a time to go back to that original position of being just relaxed. And so that moving back into the original position generates a voltage after the transmitter has turned off. So transmitter is on, generating electricity through the ground. And there's, in our case, lovely disseminated sulfide ore body. And that disseminated sulfide polarizes. So the positive ions go to one side of the ore body, the negative go to the other. Essentially, we get this polarization effect. And then when we turn our transmitter off, it depolarizes. So our positives go back and they spread back through the ore body again. So they basically get mushed around again. So they're all randomly distributed again. And they go back to their static state, if that makes sense. And so we get this voltage that's left over because of that. And so yay, we found it. But if there's nothing there, nothing that polarizes, this is what it looks like. Don't get any voltages in the ground. More often, the ground acts something like this, and we spend a lot of time trying to figure out where the different sources are. So one thing I'd like to go through, because I've got time, is you don't deal with IP data much. You might deal with EM data a little bit, but you won't deal with IP data. This is what IP data looks like. It actually doesn't make much sense. You can't drill on it. You will deal as a geologist with IP models. They are not data. Don't get confused, because if I ask for the IP data, 9 times out of 10, I'll get models sent to me, and I can't do anything with a model. Model is just a fictitious representation of maybe what could have possibly caused that particular IP response, but possibly didn't, okay? So raw IP data, I should have said, is meaningless to you. It's useful for me, but not for you guys. So what do we do with that to make it into something useful that we can drill? We do something called inverse modeling, where a computer iteratively tries to find an Earth that might have caused that data. So basically, it just makes lots and lots and lots of guesses really, really, really fast until one of those guesses matches what was actually observed in the field. So there we go. This is what the raw data looks like for this particular model section. And wow, look, this is a small BHMS deposit. And it turns out these about 180 meters below surface. So it's done a pretty good job. And that's the chargeability. The units of chargeability are milliseconds or millivolts per volt. So that is a model. Why is that important to understand? Because I can make up anything I like with models. They are completely flexible, is the best way. So models are ambiguous, models are very coarse, partly because just the nature of IP, and models are non-unique. They are plausible solutions. All of these models fit the data. And you can see how the big variations between them. And that's just because I've run the model slightly differently, making basic different assumptions about, for example, what do I think is going on in the background? How much noise do I think there is in a data? This is a nice one where you can sort of see, well, these features are fairly well resolved in all 4 of the models, these 2 features. So therefore, I'm pretty sure that they're real features. There's the same thing. This is another one where I've actually told the model I want you to maximize vertical structure, maximize horizontal structure. And you can see all of these models also fit the data. So when you get a geophysical model, you need to know what she's done. Has she assumed that you've got lots of vertical structure and applied this type of filter to your model. So inevitably you'll only get one of these. And so they're asking questions about the models is a really good idea, because you want to know, has she just tried to make it really, really smooth, or has she tried to maximize vertical structure? And I'll show you later on why that's important. Well, actually, I won't show you later on. I'll show you in the very next slide. Okay, inversion modeling is hard. So this is the bog standard inversion model that we got from the IP contractor. This is a 50 million ton VHMS, only at 350, 400 meters below surface. Could you drill it based on that IP model? No, that model is complete garbage, basically. But if you'd just gone with what was default delivery model from the contract, which is really often the case for IP, you wouldn't have discovered that ore body. You would have drilled probably this thing and maybe that thing over there. This is actually the final model that, after much modelling, we came up with. And unfortunately, in my presentation, the things moved. But basically, this anomaly is the anomaly that was drilled. This is a peridotite. We're not interested in this. This is some disseminated sulfides. This was the one that was drilled, and that was the discovery hole. So why? That's a 50 million ton. Why didn't it make a better response is the other question. We still detected it and we discovered it based on that IP, but I mean, it's 50 million tons, it's ginormous. Why didn't it make a better response? And that's because of the resolution of IP, which is terrible. IP has terrible resolution and it gets rapidly worse at depth. So at 400 meters below surface, something has to be really, really, really broad to be detected with IP, and VHMSs typically aren't that broad. So in this case, this is a good example here. So we've got two fictitious ore bodies, say 200 meters wide and 200 meters apart. We're going to do 2 IP surveys over them. Both IP surveys, this is a pole-dipole and a dipole-dipole survey. Both IP surveys find the ore bodies. Well done. Great. But these are only 100 meters below surface. Let's move them down to 200 meters below surface. And yeah, sort of find them. Not really. You know, this is a pretty low amplitude signal, given the that's only about 10 millivolts per volt. I'd say most background rocks have got about 5 to 8 millivolts per volt sort of. This has no geological noise, this model. This is a perfection where the geology is completely boring and yet we barely detect the ore deposit. So whole dipole does a slightly better job because it's better at getting energy deeper. Would we know that there were 2 different ore deposits? Maybe not. Might drill straight down the middle and not actually intersect either of them, thinking that it's just one zone. Terrible resolution. So IP detects alteration halos. It is very low resolution and is expensive. It maps disseminated sulfides, not massive sulfides, but you do get some free map of resistivity and can be useful for mapping lots of other things. Even some sulfides are also useful as because they show low resistivity zones. Why would we do it? Because most ore bodies are surrounded by an alteration halo that is much bigger. So an EM is looking really for only the really high grade core, which can be a very, very small target, where the alteration halo around an ore body is much, much larger, and that makes it an easier target to resolve at depth. So IP can often have better depth investigation for some things than EM. So if you don't think you have an alteration halo and your target is small, then IP is probably not the thing to be picking. Or if you think you don't want to have lots of possible anomalies that you're not sure are just barren geology, if you want to have a more definitive target, then maybe something like EM would be more appropriate. So this is the fun part, which is always fun to see if it works, firstly, but then it's fun if it does work. So we are the exploration team, and we get to be interactive because I'll be giving you information and asking questions, and you need to answer them. So at each of the polling slides, Danae should buy this little doobalaki, little symbol. We'll start a poll. and you'll have to answer it. Now, it's anonymous. There's no right answers. There's only better answers. And honestly, there was actually multiple ways to have discovered this particular ore deposit, but I will show you what was actually done in real life. And the aim really is to see the thought process, so you see that when I'm working on an exploration process, what sort of things we're thinking about, because I'll talk you through some of the questions that were sort of thought about. Okay, so basically you've got two options, EM and IP, all right. A fractured fantasy based on a real life discovery near Cobar. And it is obviously fairly closely based on what actually happened. So we are a small cap explorer. We've just amazingly picked up this vacant ground quite close to Cobar. It's on a highway. It's got really good gold and copper, a recently closed mine. It's close to other really significant deposits. And being on a highway makes it a pretty good prospect as well, because you've got really good access. But markets are tight, and of course you have no money, so $400,000 doesn't go for much, really. First step, open file data. So this is reduced to pole magnetics from the government, from the New South Wales government, and those obviously the existing mineral occurrences along these different magnetic lineaments. They're not actually associated with the magnetics. Note that it's reduced to pole magnetics, not TMI. There's been very little filtering. The actual magnetic variation isn't that strong, only about 55 nanoteslas. That's a knot. We've got a couple of other occurrences over here. So there's lots going on. This is that little mine that recently just closed. Lovely mine, quite a good one, but obviously out of tonnage now. What else do we have? Some radiometrics. Well, it's not exactly cover-free. Radiometrics is only seeing about 40 metres into the ground, 40 centimetres, so that's not doing us much good. There is some old IP which shows that the known mineralisation is actually highly chargeable. So good IP response. So doesn't cover this area of anomalies of workings, of old workings. So let's see if we can launch the first poll. So the known mineralisation produced a good eye response, clear evidence that it continues to the northeast. What should we do? We could do more geochemistry, or maybe detailed reinterpretation of the regional magnetics. It's already been done once. Or we could extend the IP survey along strike. If you're thinking about doing the IP, is the poll actually showing? Good, because I can't see it. And when they've finished, when you've got a significant fraction of people answering, you can just give them a couple of minutes. Yeah. You have to launch each one of the things, I think. Yep. Yeah. I mean, it's a lot of money, $50,000, but we know our mineralisation is chargeable. This is by far our best option. These little workings, let's do some IP. Yay. We do some IP, it doesn't really show much. And while it would be nice to extend further along strike, the IP contractor basically says things are getting less suitable for IP. And they advise against doing any more IP in that direction. So they don't really think we should continue doing some more IP. This is a really, really weak anomaly. It's nothing of any interest. So why do you? And so I agree that the results aren't looking like we should continue doing more IP. Why do you think I could say IP conditions for IP are getting less suitable? And, you know, you don't have to guess. Normally you would just ask me outright, but I'd just be interested to see what was the, when they finish answering that one. Yep, that's exactly right. Yeah, so target zone is getting too deep. So magnetic fields don't affect IP. We don't map magnetite with IP or magnetic fields, but the thing that really does happen to IP is if the overburden is getting too thick or too conductive. And that means we're not actually energizing the basement. So as much as we might want to continue our IP, there's no point because we're not going to be mapping the basement. The other thing that sometimes happens in this part of the world is you do get real problems with landholders. So that has to be managed very early on in the exploration process. So back to the drawing board. We didn't find anything. We spent 50,000 of our money plus a bit more. So we have, this is our magnetics. Now this is a much better display of the magnetics. This has been filtered with a high pass filter, 1 kilometre width, to remove those very deep signals so we can only see the sources of magnetic anomalies in the near surface. I would say that there's some clear, strong anomalies. This is actually a prospect up here. It's pyrrhotite causing this big, strong, you can't see that, sorry. There's pyrrhotite causing this anomaly up here, a big blob of pyrrhotite essentially in the ground, and all these disseminated pyrrhotite, which is really common in the Cobalt region, and all sorts of other things going on. So this is what the magnetics, always look at them in the grayscale, and a really good thing that you can do in the magnetics, a good worthwhile thing to do is to flip the color scale. You can see here, so this is the image with color scale, normal color scale, and this is with the flipped color scale. So why do you think flipping the color scale highlights some magnetic features that were not previously visible? I'm sort of giving you some hints in the answers here. Oh, that's a good one. I'm not doing a short course on magnetics today. Yeah. Let's hopefully see. Hopefully they figured it out. Yeah, so remnant strongly reversely polarized magnetics anomalies show up as high. So just because it's blue doesn't mean it's low. Blue can mean negative. Do you understand the difference between low is no and negative is strong, but just in the opposite direction. So always look at flipping your color scale. Notice this little, wherever my mouse has gone, there it is, this little sort of thing shining up over here now near this little prospect, and that mineral occurrence, that sort of says there's something, maybe something going on over there as well. So what to do next? Well, we really haven't got anywhere. We've just shown that there's nothing in a short interval past the known ore deposit. There's only 300,000 left in the budget now, and you can only choose to do, we can go and drill some mag targets. We can afford to drill about 4 holes. The width of the tenement's about 20 kilometres, so that's fairly risky, I would say, 4 holes on a 20-kilometre area. Oh, the neighbours are doing some VTEM. We haven't really come up with many ideas so far. We could do some more surface geochem to try and willow down our area of interest, or bail out of this tenement, which we've already spent $100,000 on. What's our online audience think? Tag onto your neighbour's beach. That's what I would do. $30,000 is pretty cheap. Most airborne surveys cost about $300,000, right? But because they're flying next door, bonza, you know, you just basically pay the line kilometre rate. Done. Nothing, yeah. On mapping, yeah. No, we don't like sending actual geologists out in the field. So we choose cheap. I mean, $30,000 to cover is pretty good. Yeah. So can't cover, for $30,000 you can't cover the whole area, but you can pick this area, which obviously we have identified as being interest. And you know what? We had that little mag anomaly over here. We had these couple of old workings over there. So we fly those 2 areas. And there was obviously some geologists didn't get involved at some point because there's geology and silicification over in this area. So they knew something about that area. So this is the VTEM, and that's on the map. So we've got some airborne EM. Should you display it in this format? You can display it. Should you do an interpretation based in that particular method of displaying it? No, that is just to show really where you've done the EM and some broad pictures like where you've got overburden, not overburden. But You can display it, but don't do your interpretation based on that. You also get free remember that magnetic anomaly? Here it is here. Remember that little like magnetic high that was, or magnetic low was actually a magnetic high, showing the fact it's a magnetic high you can pick up by the contours. It's hard to see in this format, but the blue contours in this blue area are widely spaced. That's because there's no magnetic signal there. And here they're closely spaced because that's a strong reverse magnetic signal. So the contours themselves also show you where you've got magnetically reversed anomalies. So strong positive, strong negative. So that's that little mag low. So lovely free mag intense map. And then there's a EM response channel 20, which is one of the middle time channels, not the early time and not late time. There's our flight path. And let's look at our VTEM data. So there's a profile here. I can see the early time shows we've got overburden, quite a strong overburden response here, not much overburden response, and then a bit more of overburden response over there, some over there as well. So this is just generally looking through the profile data. This is what the VTEM data looks like. Early time is the top channels, bottom ones are late time, and the ones in the middle are middle time. Yeah. Okay, this is a fun one. Where's Wally, the anomaly? You have to pick on these profiles where it is. I find actually geologists usually do a pretty good job on this one. Do me out of a job. What, do we have any votes on this on our in-person forum? Yeah. Yep. Well done, guys. That's the anomaly right there. So the late time channels, not a great anomaly, but a clear anomaly still. A few other anomalies. We found some anomalies associated with this pyrrhotite. Yay. But this is the best one. It's right next to that reversely polarized magnetic anomaly. So this is the good EM anomaly there. Notice that we can't even see it in the channel amplitude grids. It doesn't even show up in that, because the channel amplitude is heavily biased by what's going on in the overburden or other things. You really can't see it. So don't do interp off channel amplitude grids. You get them for free. If you know exactly which channel to look at, you can usually see the anomaly, but you really need to know what you're looking at. Doesn't really show up, doesn't really show up, doesn't really show up. Oh, there it is. So I knew where to find it and what channel, but yeah, it's really hard. Don't use those channel amplitude grids. There it is there. Lovely, we found the anomaly. So rank these statements. This is a different type of interaction. Hopefully you can do that. Did you do it this way? Yeah, good. So you guys know the answer to A now because I've drummed it in. Don't use the channel amplitude grids, all right? But how about B? Can we drill that red blob that we found now that I've shown you where you can see it on the channel amplitude? Can we drill it just like it is? Are the airborne contractor being realistic when they say they've reported when they say they've, well, we will have mapped something down to 400 metres below surface or 800 metres below surface or any of these claims that we often get? And no, we can't. Which one are you referring to?
They're reporting 400 metres depth.
When they make these claims, it's normally based on basically they fly over a deposit, say a particular deposit at normal survey height, and then they fly over the exact same deposit but move the airframe up to 400 metres above the surface, and they say, look, we've seen it twice. But there's a big difference between air and rock. So, and then that's not even your survey area, and it's not your size deposit. So depth investigation is proportional to size, and it's also proportional to your local geology. And pretending that air is the same as rock is not mathematically appropriate. So yes, technically they can see something 400 metres away from the survey frame. Is it a realistic estimate? No. All right, so what do we get? VTEM data does not need expert interpretation. Hopefully that's got a very low likelihood. How about peak of the anomaly directly over the source? That's right. The peak of the anomaly is not over the source, except for unless very horizontal, flattish ore bodies. Are we being realistic if we expect that we're detecting something at 400 meters below surface? No, that's, yeah. And VTEM is routinely used exploration for porphyry copper. That'd also be a no. I just put that one in there for a kicks. So we have some VTEM. Can we skip this one? I will just explain it instead of not actually doing the poll on this one. Okay, so EM data. This is EM data. This is not EM data. This is something called a resistivity depth image, and it basically tries to take EM data and turn it into a pretty picture. Now, the actual conductor in this case is exactly between these two red blobs. Where would you drill? Any reasonable geologist would drill at these red blobs, right? Because they don't give you these sections with an explanation of exactly what they are. You'll get them for every project you do, airborne, mouse, and you'll give you red blobs. There's also one down here. This is related to errors in the airborne data. It's not an anomaly. And this is related to the fact that this is a 1D algorithm and EM data is 3D, okay? You have to model. If you want to drill something based on EM data, you need to model it using a plate conductor. Now, the way you'll run into these most of the time is if anyone's using any of the airborne EM curtains in the MinView websites, you know, those lovely airborne EM curtains where they've done the big regional airborne EM surveys. That's what these are. And people are drilling things like this and that. And if they're drilling it in the wrong location, and it's probably just errors in the data anyway. So be really careful with any EM that looks like a pretty picture. Needs expert interpretation. So we've burnt through a fair bit of our money now. We have an airborne EM anomaly. We don't really know where the source is. How are we going to drill it? And that's a really hard question. We could do ground EM to get survey, but we don't have much money. We could try and model the VTEM directly and then drill it. Still running out of money. We could just drill it. Okay, what do you reckon we should do? We don't have much money left. And none of, like, each of these are definite options, all good options on the table. The problem with ground EM is it's going to cost money. And that's also modelling the VTEM directly is also possible, but maybe the anomaly is not strong enough. And that's, if you're going to model VTEM directly, your geophysicist should say this anomaly should be able to model or can't model. Some geophysicists will just always do ground EM survey. It could be the world's strongest anomaly where we can tell exactly where it is from the airborne EM, and yet they'll do a ground EM survey, and I'm not sure why, if it's a make work thing or a risk reduction thing, I don't know. But sometimes you can just drill directly from the airborne EM. What did we get for that one? That's probably what I would do for this one. And so I did it post-haste. I actually tried to model this response post-haste. Now this response unfortunately falls into the not strong enough camp. So you can see I can fit a plate model dipping that way and a plate model dipping that way. They're both data. So in other words, there's not enough information contained in the VTEM for me. So how do you drill something? It's pretty hard to plan a drill hole that can test both of those models. Maybe you guys are cleverer than me. So I'd probably say, yeah, we could have gone that way, but it might not have done what we wanted to do. So, and that's why we all care about noise so much, as the lower the noise, the more likely we are to just be able to drill it directly. So you could miss it with a drill hole, but that probably would have got you there. So you actually choose, I only gave you three options. What they chose to do was do a single line of ground EM to confirm that it was in fact an anomaly, not some weird like error in the VTEM, and then not model it. They didn't model it. They just guesstimated where the source was and then drilled it. we'll see what happened with that particular approach, which is slightly novel. And we'll skip this one as well. Go to the next one because I'm just aware of time. Yeah, so drill hole, they drilled this model based on the guesstimated location and got essentially nothing, all right? Now, so they drilled another hole. We're not there's certain points, things that could have happened. I'm sure you can guess what they are to confirm that there was nothing there. Right, so drilled first hole, drilled second hole, still got nothing. Let's do this one. So what do we think is going on here? Do you think that low-grade sulfides that they did intersect are sufficient to explain the VTEM and fixed loop BM anomalies? We know it's not a false VTEM anomaly because that's why we did the grounded EM to confirm it was real. Maybe the hole's missed, just a possibility, okay? Or at this stage, we don't have enough information to answer this without spending more money. Yeah, it is true. At this stage, we don't have enough information. So let's do some more work. So we'll skip this poll. We could model that EM. That would probably get you there. If you compare the modelling of the EM with the drilling, you might understand what's going on. But there's actually a bigger problem. No one's actually surveyed the drill holes to work out. So we think our drill holes are in a straight line, right? But maybe they're not a straight line, okay? We could do another fixed loop EM just to confirm the first loop fix. It seems like a big waste of time to me. Do downhole EM to see if the hole is actually missed. And that would show you if it's missed, or maybe, or you could just give up and say this VTEM stuff is a waste of time and, you know, geophysicists are all snake oil salesmen and, you know, rah, rah, rah. They do a downhole EM survey. Well, downhole EM, because the probe actually has information in it, because we can actually work out just by the way the fields behave that the hole's bending. And so I wouldn't use downhole EM to do my whole azimuth stuff, but if at the end of the day we can do that. So the downhole EM would have showed, and it did show, that they'd missed the conductor, not just by a little bit, by like a long way. So it works out to be about 100 metres away from the drill hole. They've missed it by about 100 metres, which is a pretty significant miss. But the downhole EM can still see it. It's pretty good. They do downhole EM. We could model that downhole EM or not. Just drill another hole. So what they did instead was drill another hole. And guess what? Missed again. So, but the downhole EM, that shows that you're much closer. Right. So we're getting there. You can imagine management are getting antsy now, because remember we had 60,000 about 3 holes ago. We have no money, yeah? So about 50 metres off hole. Once again, none of these holes having dipped an azimuth survey, and that's really the problem. So 3 holes in those 2. Do we want to run this poll? Do we have time to run this poll? Yep. You can give up and find a new career. Arrange to get the fixed loop EM and downhole EM model. And really that was, in this case, it was because the geophysicist on this project wasn't really an EM, didn't physics, and so it wasn't easy for him just to smash out a quick model. So it's a case of, you know, people involved, like technically an excellent geophysicist, but maybe hadn't needed to would have had to farm out to someone else, and short time frames, budget considerations just didn't happen. So that's part of the reason that this hasn't been done already, but they did. They should have some answers now. They arranged, they got the fixed loop EM and downhole EM modelled. And sure enough, oh, look, there it is. I actually modelled that data because I didn't have the downhole EM models that they based on. So I modelled that fixed loop EM data only, didn't even bother modelling the downhole EM data. So that's just the model based on the fixed loop EM. And this is the discovery hole here. So that's actually Malibu, and I'll show you how close. So you can see that all the holes drilled before they got to number 6, okay? And you can see a lovely strong intersection response, off-hole response, intersection response, and a downhole EM. So we found it. So the fixed loop EM, this is the ore. I didn't have these ore body models when I did the model of the fixed loop EM. That's just my conductor there, and you can see how well it corresponds in dip and location with the actual location of the top part of the copper zone. Note that I don't actually get the depth extent right, and that's because we're not really seeing that with a surface EM survey. You'd need to have some drill holes going through that, and with downhole EM for me to model that. It does a really good job finding the copper, utterly fails to find this really lead zinc zone in the hanging wall. So shows you what the EM is really mapping in this case. So that's malleable. Yeah, if we could have found it using mag if we drilled enough mag anomalies, which with 4 drill holes might have not got you there. But if you'd just gone out and drilled all the little mag anomalies, probably would have found it eventually. Interestingly, there's disseminated sulfides everywhere. So when you do IP, you find lots of disseminated sulfides, and many of them are much bigger than this particular deposit. So whether or not you would happen to drill this particular IP anomaly of all the IP anomalies, that's maybe debatable. See, there's a model of the mag. So yeah, you probably could have eventually drilled it with the mag. There's all these ones over here. That's Butcher's dog. MT, magnetotellurics, no, because the strike length is too limited for magnetotellurics to really show the ore zone. And if you'd done a regional scale ground EM survey, you would have discovered it. As long as your line spacing was approximately about 200 metres, then that's enough to get at least one line over the top of malleable. So line spacing with EM is proportional to strike length. Anyway, so thanks to Peel Mining for permission to use this data. Sorry for all the mistakes. Rob Tyson and Steve Collins, who was the geophysicist on this project. And of course, as Steve would say, providence, luck, perseverance, I say. Yep. Right, guys, I won't go on to the second case history because we've run out of time, but I'll just summarise with the 2 slides at the end of the presentation. So tips for effective integration of electrical geophysics. So you need to think about your exploration model. What are you actually looking for? If you're not expecting massive sulfides, then EM might not be appropriate. If it's too small compared to its depth, IP might not see it. And remember that old models are guesses. They're variable and they're very, very, very coarse. Don't confuse the model data with the data, but do use them. Don't also drill a single anomaly in your model and go, that's it. We've tested the geophysics in capital G for geophysics, right? You drill more than one hole. There will be multiple anomalies usually. Just because one hole is disseminated sulfides doesn't mean that the rest are going to be. You don't need to be an expert in geophysics, particularly electrical geophysics. I don't expect anyone I work for to be an expert in it, but you just need to know them, and you need to know to ask questions. Just basically ask questions. Just keep on asking questions until you understand, because there is literally no dumb questions. And so it greatly expands the search volume and delivers bang for buck. So yeah, good. All right.